Hello, everybody. Welcome to section 2.4. This section is going to be on average rate of change. So first off, what is average rate of change? So the average rate of change of a function f of x between x equals a and x equals b. So that's between 2 points a and b, is given by the formula. I'm going to use ARC as sort of a shorthand for average rate of change. That's going to be change in f of x over the change in x. In actual symbols, that's f of b minus f of a over b minus a. Cool. So some of you might notice this looks very similar to the formula for finding the slope of a line, right? Where we had rise over run. So that's because if we look at like a graph of a function, so if we look at x and y, we have some function here. Let's do something like this, make it wiggle. And let's say we had this right here was a, and this right here was b. So we have x. The average rate of change is describing, if we look here, a, b, the average rate of change is describing the slope of the line between these 2 points. Okay. So this is all fun and fine, but why do we care? So why do we care about average rate of change? Well, two main reasons. First, and most practically, we can use it to understand complicated function behavior. So if we have a function and it's really messy and we don't really understand what it's doing, what's going on, we can sort of use the average rate of change to sort of get sort of a handle on what it looks like, or at least how it behaves. And the second point is we can use it to approximate phenomena. There are other reasons why the average rate of change is important, but these are the main ones that we care about in this class. So let's see some examples of calculating this. So calculate the average rate of change between x equals 0 and x equals 3, 4. Let's do something simple like f of x equals x squared minus 2. So simple polynomial. The average rate of change, according to our formula, is going to be f of 3 minus f of 0 over 3 minus 0. And if we plug in 3, we get 3 squared minus 2 minus 0 squared minus 2 over, just that simplifies to 3. And we have 9 minus 2, and then this minus distributes into here, so we get plus 2 over 3. Is that right? Yes. And then we have 9 over 3 is 3. Okay. Cool. So now let's look at another function. Let's do maybe g of x. Let's look at something maybe a little more complicated now. Let's do x plus 2 over x minus 1, and then let's do x minus 2. All right. So our average rate of change is going to be plug in 3, subtract from plugging in 0 over 3 minus 0. And then if we plug that in, we get, let's see, I think it's, we're going to get absolute value of 3 plus 2 over 3 minus 1 times 3 minus 2 minus, and then absolute value of 0 plus 2 over 0 minus 1, 0 minus 2, all over 3. As you can see, these problems are mostly computationally heavy. There's not a lot of creativity involved in the solutions of them. So they're fairly straightforward, which is nice. And so I believe this becomes 5 over 2 times 1 minus 2 over negative 1 times negative 2, all over 3. And then that gives us, 5 halves minus, and I'm going to leave this as 2 halves, so I can actually subtract them. And that'll give me 3 halves over 3. And then that you can simplify to thinking of it as 3 halves times 1/3. These 3's cancel, and we get 1/2. All right, cool. So calculating average rate of change between 2 points for a given function is pretty good. But we can use it to understand things that are more complicated, much more complicated. So let's look at an example of that. So the temperature of, let's say, a thawing ice block in Celsius is given by this following function. Tm is going to be 20 over 1 plus e, which I'll explain in a minute, to the power of negative 0.2 times x minus 30. So this is a nasty function, right? First of all, it's got that e in there. E is what's known as the growth constant. It's about 2.72. And it's got x and an exponent, and then there's a fraction. This is, it's a mess. Okay. But the question wants us to know, so first of all, where m is minutes. So this should actually be m in here. There we go. The question wants to know what is the average rate of warming between m1 equals 0 and m2 equals 30. So we want to know what the average rate of warming is between time 0 and after 30 minutes. And this is what average rate of change is exactly useful for. So we can talk about what, or rather, how warm this ice block is getting over time on average, right? So we're just going to calculate this using average rate of change. We're just going to do T of M2 minus T of M1 over M2 minus M1. And so if we plug our M's into our functions, so we let M1 be 0 and M2 be 30, blah, 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 we get 20 over, and then this becomes 1 plus e to the negative 0.2 plug in 30 for that, minus 30, minus, and then that's going to be 20, running out of room, plus e to the negative 0.2. So it'll be 0 minus 30. That's all going to be over 30 minus 0. All right. Then we have, if we simplify a little, 20 over 1 plus 30 minus 30 is 0. So this becomes e to the 0, because 0 times 0.2, even if it's negative 0, minus, and then on this side, we still have 20 over 1 plus, and if you do this calculation out right here, you should get e to the 6 all over 30. And then if we look at this a little more closely, we simplified a little bit more, we get 20 e to the 0 is something to the 0, so that's just going to be 1. This is 20 over 2 minus, I'm going to leave this as 20 over 1 plus e to the 6 over 30. And so then this becomes 10 minus 20 over 1 plus e to the 6 over 30. Now, if you plug this into a calculator, you get that it's about 10 minus 0.045, very small number, over 30. And then if you plug this into a calculator, you get that this is about 0.332. So the average rate of warming between time 0 and 30 minutes was about 0.332 degrees Celsius a minute. So we took this really complicated looking function up here, this nasty looking thing. And what we did is we approximated it and approximated like how it changes using ARC, using the average rate of change. So we kind of got a grasp on this this phenomena using a much simpler technique than trying to understand what the function is doing just in its entirety, right? And this is the actual formula for warming and cooling. Like, this is Newton's law of warming and cooling. So we did some real world analysis on this function. Cool. So that covers average rate of change and sort of its main applications and how to use it to solve problems. Keep working on your homework, and I hope to see you in office hours.